developing next-generation research and technology, facilitating connections between AFRL industry and academia, unlocking innovation through a culture of collaboration. This is the AFRL Regional Network Midwest.
Hello, I'm Aditya Nechiyil, co-founder and CEO of ResCav LLC. Our team is tackling the challenging issue of detecting tampered integrated circuits, or ICs, which can compromise the safety and reliability of critical systems and infrastructure. Current available methods for the detection of tampered integrated circuits can often be slow, ineffective, expensive, or even destructive. Our goal is to address these limitations with the development of the ResCav system, a non-contact and non-destructive solution for the rapid screening and detection of counterfeit or tampered ICs. Our current experimental setup consists of two key hardware components, the resonant cavity and the vector network analyzer. In this project, we aim to evolve our current experimental setup into an enhanced prototype to incorporate additional components and an intuitive graphical user interface that will allow for the seamless integration and operation of the entire system. Since starting the project, we have designed and integrated the hardware and software components for the new ResCav system from the ground up. This system allows us to rapidly capture a unique fingerprint of the IC when it's placed inside. This fingerprint is unique to the structural and material properties of the IC and is even sensitive to the design changes solely made to the silicon die. These changes are not visible through traditional non-destructive inspection techniques such as X-ray imaging. The process to capture a signature is very straightforward. Simply open the system, place the IC onto the holder, close the system, enter the details of the IC, and capture the signature. All of these operations and more, including displaying the signatures and performing statistical methods such as principal component analysis, can be seamlessly done through the graphical user interface, or GUI, that was developed for this project. Breaking down the hardware components, we firstly have our newly fabricated resonant cavity. The cavity was precisely machined using aluminum 7075. Within it is an electromagnetic probe that excites the cavity with the radio waves, and the IC holder with the resin compliance mechanism that assures consistent placement of specific IC packages. The compliance mechanism can easily be substituted for universal compatibility with any IC package type. The cavity was specifically designed to integrate well with other components, such as the electric linear actuator, which controls the opening and closing operation of the lid. Automating this step has not only greatly improved the speed at which we are able to acquire measurements, but also increased the repeatability and consistency of the signatures acquired. Finally, we have the one-port vector network analyzer, or VNA, from Copper Mountain Technologies. The VNA, which is connected to the probe by an SMA adapter, sends and receives radio waves into the cavity over a wide band of frequencies. The complex ratio of these waves, also referred to as the reflection coefficient, is what constitutes the unique signature of the IC.
Due to the globalization of the microelectronics industry and the lifetime extension of many weapons platforms in the Air Force, being able to assure the functionality of the electronics going into these weapons platforms is absolutely vital for national security. For instance, the B-52's first flight was in 1952, and it is expected to remain in service well into the 2050s. Part of assuring the microelectronics is testing to make sure that the Air Force is getting what they purchased and only what they purchased. Projects like these will help to ensure that no counterfeit parts or parts with malicious insertions can make their way into the DoD supply chain.
We've made significant progress over the past 6 months. After designing, fabricating, and integrating all the components, we began testing the system with a focus on consistency, a key factor in performance. To test repeatability, we conducted several tests, starting with assessing the VNA's thermal equilibrium period. Like most measurement equipment, the VNA requires a warm-up period to reach stable, accurate readings. We wrote a Python script to capture measurements at 1-minute intervals from a cold start up to 4 hours. We found that after 3 hours, the system reaches thermal equilibrium with minimal error occurring after that period. Additionally, we tested the system's resilience to slight shifts in IC placement by manually repeating the process. Here, the error fluctuated, but never trended upward. After confirming the system's consistency, we performed blind tests with our AFRL collaborators using the same test articles that was used to evaluate our experimental setup. The new ResCav system, which was designed with similar specifications as the experimental setup, matched its performance, all while automating several processes. Doing so allowed us to capture signatures 3 times faster. In conclusion, the ResCav system continues to prove efficacy in detecting subtle variations in ICs, and we've successfully automated key components to streamline the measurement process and data analysis. Moving forward, we aim to further refine both the hardware and software to enhance performance and scalability. We are confident that with these improvements, the ResCav system will continue to evolve as a powerful tool in tampered and counterfeit detection for critical defense applications.